Well, hello and welcome to this Zeus webinar. My name is Rich and I'm a senior manager with IHS, and I'd like to review a few housekeeping items with you before we begin. Let's take a moment to familiarize ourselves with the operation of the user interface for today's webinar. Now, the large window with the heading Zeus presentation in the upper left, that's the primary window for today's webinar. You should be seeing the welcome slide there right now. Now, just to the right of that main presentation window, you'll see the speaker's bio window, and that contains background information on today's presenters. Just below that, there's a Q&A window. At any time during the presentation, you can enter a question into the box in the lower section of the Q&A window and click Submit. Your question will then be placed in a queue for our speakers to address when we get to that Q&A session. Now, if you look to the bottom of your screen, you'll see additional buttons to enhance your webinar experience. To see what a particular button does, just hover your mouse pointer over it and a tooltip will appear with a description of that button's function. And now to get this webinar started, here's your Business Development Manager, Wayne Black. Wayne?
Thank you for the introduction. Welcome to the webinar, Heat Shrink Technology, a world of high performance possibilities. I'm Wayne Black, Business Development Manager at Zeus. We want to thank you for attending as we have an exciting presentation lined up that will teach you about high-performance heat shrinks. We will cover how heat shrinks vary, material options, and then our core focus will be on high-performance materials used to make heat shrinks, which will lead us to discuss how they may vary in properties, methods of proper recovery, and also touch on how they may be used in key markets. Joining me today we have Dr. Irina Roof, Material Scientist, and Matt Allen, Senior Manager of Corporate Medical Accounts. Many industries operate today in demanding conditions. Products in oil and gas or aerospace can face extreme environments that range from high heats to freezing cold, to being in the constant face of caustic chemicals that make engineering designers rethink what materials are optimal for future designs. Medical device manufacturers appear not to operate in extreme temperatures. However, material selection is very important as medical devices can be exposed to high temperatures for sterilization or even radiation, which makes engineers reconsider high-performance materials to meet design goals. Before we jump into specifics, let's cover what heat shrink is and some options in the market. Heat shrink is a form of product that normally starts life as an extruded polymer tube, which then goes through a secondary process involving heat and mechanical force to expand the internal diameter to a larger diameter. As that larger diameter is achieved, commonly called the expanded diameter, the product can be cooled or even irradiated to keep the product dimensionally stable at that larger diameter. Ratios of expansion, as we will learn later, vary greatly with material. Once dimensionally stable at the expanded diameter, heat shrinks then will have locked in some forces while being manufactured, which are inherent due to the process. The finalized product then can be heated again to a predetermined temperature, which will cause the product to naturally want to migrate to its original extruded form or go back to its recovered state. The world of heat shrink is wide and varies greatly with material selection or property selection. Available in the market are a variety of coloring and coloring options such as spiral colors, high temperature heat shrinks, low temperature shrinks, some that are approved for aerospace, some for medical, single layers, epoxy lined, even dual layers. Multiple comparison options exist. For ease of display, here are some materials that vary in usable temperature thresholds and price accordingly. As you can see, there are lower performance materials such as PVC and polyethylene, and the spectrum moves all the way to polyamides and even PEEK that can withstand up to 260 degrees Celsius. Let's take a look at a few markets that utilize high-performance heat shrinks. Also, we will discuss some common applications which demand their usage. Primarily, we'll focus on the aerospace, energy, and medical markets. Planes have a lot of moving parts and even more wiring. The wire is critical, but insulation and splicing of the insulated wire is paramount. Designers should know that there are great materials that can be made into heat shrinks such as PTFE, FEP, even PEEK, which can be good insulators but also perform well in low and high temperatures, not support fungus growth, have good chemical resistance, and low water absorption. Standards such as M20353, SLAN 11 and 12 for FEP and PTFE respectively allow qualified manufacturers to certify to a standard to give aerospace design engineers confidence as well as supporting documentation. Dual shrink, The combination of an outer layer of PTFE heat shrink and an inner layer of FEP heat shrink can make an excellent splicing aid. The inner layer of FEP will melt and flow into spliced connections when exposed to the temperature required to shrink PTFE, which will result in a moisture-proof splice that is encapsulated with a dual layer of protection. Don't just think wiring though. Composite engineers often use FEP film as a release aid as it can withstand high autoclave temperatures and has excellent lubricity. Designers making parts that are round, trapezoid, hexagonal, and more should consider thin FEP heat shrink, which can save time and money without sacrificing the properties of FEP that are beneficial in the application. The energy market, ranging from oil and gas exploration to nuclear, also has critical wiring that needs high-performing insulation and heat shrinks to splice wiring. Electrical submersible pump motors utilize a variety of high-performance polymer insulated magnet wire such as polyimide and PEEK. PEEK can be a good wire insulation choice as it is very abrasion resistant and has a high strength to weight ratio. Engineers will be well suited to consider PEEK shrink for wire splicing as it has a dielectric strength of over 3,000 volts per mil with a 3,000th wall thickness, and if recovered properly, can make what is normally the weakest point of wire, the splice, into one of the strongest due to PEEK's inherent properties. It can also speed up manufacturing of splicing by using heat shrink versus a tape wrap. The process is robust and easy to implement, which can potentially reduce operator error that is common with tapes. Rock core sample preparation can also be a common application for performance heat shrink. FEP heat shrink can be used to easily encapsulate core samples that can be sealed and stored in order to do analysis of properties such as, but not limited to, stratigraphy, volatiles, and voids. Don't just limit those to samples of Earth. NASA engineers may want to consider high-performance heat shrink such as FEP or PEEK as well for missions on Mars or other planets that require rock core and soil samples to be attained, transported, and later analyzed. Now here's Matt Allen to discuss in detail some medical applications that may use performance heat shrinks.
Thank you, Wayne. In the medical world, heat shrinks are used in a variety of markets and devices, being used as both manufacturing aids for reflow, as well as remaining on the finished device for patient contact. Starting with PTFE heat shrink, two of the more sought-after features are its superior dielectric strength and low coefficient of friction, both of which make this material the ideal candidate for use in the gastrointestinal endoscopy market. PTFE sublight wall spiral striped heat shrink is used as a guide wire coating due to its lubricious nature, allowing doctors to navigate the most tortuous pathways. The spirals allow doctors to visually see any movement of the wires, and every positioning is required during a procedure. Snares and forceps shafts can be encapsulated using PTFE heat shrink as electrical insulation. PTFE heat shrink benefits both the device and the patient by providing electrical insulation, a lubricious surface, and moisture protection. Laparoscopic instruments are an example where FEP heat shrink can be used to coat the outer shaft, allowing for insulation between the patient and the device as it cauterizes tissue. The typical construction of a catheter consists of a mandrel, PTFE liner, braid or coil, encapsulated with a nylon or PVAX extrusion that is reflowed using FEP heat shrink. PTFE sublight wall heat shrink can be utilized as a liner in a catheter application when the need calls for a tapered design. Due to PTFE's low coefficient of friction, the outer diameter would need to be chemically etched in order to allow other materials to bond. FEP heat shrink is used primarily as a tool by sliding it over a PVAX or nylon outer jacket material and then recovering it around 400 F. Keeping in mind the dwell time and temperature can be adjusted for each application for optimum yield. The recovery temperature of FEP heat shrink is above that of the outer jacket, therefore allowing the outer jacket material to reflow down into the braid, making contact and bonding to the PTFE liner. Once removed, typically with a razor blade, the FEP heat shrink's smooth, void-free ID leaves behind an outer jacket with a smooth, uniform surface finish. In more complex catheter construction, such as cardiovascular or neurovascular, this critical step works twofold, not only bonding to the PTFE liner, as previously mentioned, but also allowing a smooth transition between the multiple durometers along the catheter shaft. This is the industry standard and has been since the emergence of cardiovascular catheterization. Advancements in minimally invasive surgery has led to the more complex procedures requiring lower profiles, softer durometers, and smaller diameters. Although the basic building blocks to construct a catheter are the same, working with soft durometer and small diameter materials has created its own inherent manufacturing challenges. Reflowing these more delicate underlying materials, or when reflowing small diameter materials, it can be challenging to remove the FEP heat shrink without damaging the underlying material, causing yield loss and scrap. Due to these challenges, the industry has been asking for a peelable heat shrink, and not until 2014 has anyone been able to provide a solution. Fluoropeels, a peelable heat shrink with properties similar to FEP heat shrink, but with more optical clarity, was developed as a solution to this industry challenge. It can be used as a manufacturing aid, just as FEP heat shrink was described in the catheter construction using similar recovery time and temperatures. However, when it is time to remove the fluoropeels, you simply notch one end and longitudinally peel continuously down the length, therefore reducing scrap, increasing yields, and improving employee safety with the reduction of razor blades on the production floor. Now, here is Dr. Arena Roof to discuss in detail the materials and their high performance properties.
Thank you, Wayne and Matt. There's truly a world of possibilities with heat shrinkable materials. Here we have a comparison of different materials, ranging from lower cost, remedial performance, all the way to even though more costly, but extreme performance characteristic materials. On this slide, we are comparing polyethylene to some of the fluoropolymer family heat shrinks, as well as peak shrink. From the material selection standpoint, it is important to know what performance attributes are essential to your application. Here we have summarized a few of those. On a previous slide, you saw a visual representation of temperature performance of these materials. Here, we organized them in a similar manner. However, we added dielectric strength and chemical resistance. Class 6 approval data is also listed. As you may see, each material has its advantages and areas where it outperforms others. For instance, peak shrink has exhibited extremely high dielectric values of up to 3,500 volts per mil, as compared to, let's say, polyethylene with barely any dielectric strength. Highly engineered polymers, such as PTFE and PEEK, will outperform lower-grade plastics on chemical resistance as well as temperature withstand, thus making materials more useful in highly demanding environments where caustic exposure is inevitable and high-temperature performance is a must. Another challenge, especially for medical applications, is sterilization response. This table summarizes plastics performance post-sterilization. Although PTFE is superior to most materials in chemical resistance, if your use calls for sterilization of the system using gamma radiation, PTFE may not be the best heat shrink to utilize. On the other hand, FEP and ETFE withstand high energy ionization much better. PEEK is most definitely the best reformer with highly penetrating gamma rays. Frankly, it can withstand up to 1,000 megarads of radiation before its mechanical properties begin to compromise. In comparison, PTFE is only rated to 1 megarad of the same exposure. It is important to remember that gamma sterilization is not the only way of sterilizing by irradiation. Electron beam is one other method used rather frequently. Because of the inherent similarities of these two methods, most materials slated to be poor performers under gamma conditions remain less than excellent performers under E-beam. As you may have noticed already, there is a lot of considerations to be had when choosing the right material for the application. Let's dive a little deeper into all of the aforementioned high-performance heat shrinks. Let's begin with PTFE. Polytetrafluoroethylene, or PTFE, is a polymer which is comprised of the tetrafluoroethylene monomers as briefly shown on this slide. This polymer contains carbons and fluorines in its structure. PTFE is synthesized from the tetrafluoroethylene monomers which, when combined, create an arrangement containing covalent bonds between carbons and fluorines. The structure of the material, as one would imagine, is linear in nature. However, it is better described as rod-shaped. Because of the size of the fluorine atoms, the carbon-carbon backbone is bent in such a way that it forms a spiral shape with approximately 30 atoms to make a full 360 degrees turn. Also, size of the fluorine atom allows for a continuous sheath to be present around the backbone of the polymer. The molecule which is formed is linear in nature with no branching or other side groups and resembles a cylinder with carbon core and fluorine outer layer. It takes a lot of energy to disturb the polytetrafluoroethylene structure because of the length of the carbon-fluorine bond and its allowance to, so to speak, blanket the carbon backbone with fluorine atoms. Solvent molecules cannot penetrate the sheath, making PTFE extremely chemically inert. Alongside, PTFE has the electronic balance and neutrality to further repel any foreign substance with which it comes in contact. So, the characteristics of fluorine atoms and carbon-fluorine bonds allow PTFE to possess very attractive properties, such as high melting point, high thermal stability, low solubility, low friction, and extremely low surface energy. There are no known solvents for PTFE below its melting point. It is, however, attacked by molten alkali metals, chlorine trifluoride, and gaseous fluorine. Although PTFE doesn't flow, its melting point as measured is very high, upwards of 320 degrees Celsius, which allows this material to have outstanding performance at extremely high temperatures, up to 260 C. PTFE also retains its pliability at low temperatures with gradual change in its mechanical properties as a function of temperature. On this slide, you can see a comparison of mechanical stress versus strain curves of PTFE at different temperatures. Around room temp, 23 degrees Celsius, material behaves like a typical thermoplastic, where the elastic region extends until the yield point, after which continuous extension results in increased stress due to strain hardening and eventual fracture. If we take a look at the same relationship at negative 56 Celsius, one can see that this curve has a similar shape. However, the stress values, measured as force over a cross-sectional area, are much higher, which is to be expected of any ductile material subjected to such thermal treatment. So, PTFE retains its useful properties even as low as negative 56 degrees Celsius. However, at negative 196 C, material exhibits very typical characteristics of brittle materials, where there is not much elongation change in the material upon applied stress prior to its fracturing. Furthermore, at elevated temperatures, up to 260 C, PTFE has a tendency to become more elastic, losing its tensile strength. Nonetheless, material remains intact and continues to possess useful mechanical characteristics. So let's extrapolate all of the properties of polytetrafluoroethylene to the PTFE heat shrink. This heat shrink has valuable mechanical properties because of the material's stability at elevated and low temperatures. It has exceptional chemical resistance and good dielectric strength. It can be sterilized using more than one method. But one of the most important characteristics is that PTFE heat shrink can be produced in very high recovery ratios, namely up to 4:1. In other words, an 1-inch tube in its expanded state can be recovered down to 1/4 of an inch diameter. These high expansion ratios are essential when working with a system where the heat shrink must fit over a hub or a taper and then shrunk over the whole system, creating a tight fit and an excellent barrier. With expansion ratios of up to 4:1, PTFE heat shrink can be tailored to provide the best fit for the final assembly. PTFE heat shrink is recommended to be recovered at temperatures of around 340 Celsius. However, it is important to remember that recovery process is to be developed for each application, taking into consideration the system as a whole. In applications where a very thin layer of PTFE is needed after the plastic has been shrunk, sublight wall material may be useful. PTFE can be made with wall thicknesses of 0.004 of an inch and lower. Another PTFE heat shrink characteristic to keep in mind is its extremely low surface energy. Because of it, polytetrafluoroethylene has its attractive chemical inertness and unparalleled lubricity. Therefore, PTFE heat shrink surface must be chemically modified if bondability is required in an application. This secondary surface chemical modification, or etching, can be preserved during the expansion process, as well as it can, to a certain extent, remain potent after the recovery. A tailored recovery process would have to be developed for an etched PTFE heat shrink. Because of its linear molecular structure, polytetrafluoroethylene heat shrink can be peeled longitudinally after the recovery process. This becomes useful if the heat shrink is used in an application where it must be removed after recovery. So, overall, PTFE is an excellent heat shrinkable material for certain applications. However, the very thing that makes it applicable in so many ways, specifically high temperature resistance and high recovery temperature, can deem it unusable in other applications. For instance, a situation where the mandrel onto which heat shrink is applied contains temperature-sensitive materials. One must identify another useful plastic. Fluorinated ethylene propylene, or FEP, is a lower recovery temperature alternative to PTFE. The chemical structure of this polymer very much resembles that of PTFE. However, a branch is introduced to the linear molecular structure. FEP is a copolymer of tetrafluoroethylene and hexafluoropropylene. Seemingly small structural difference yields measurable property differences. But first, for similarities. FEP has a very low coefficient of friction. If you recall, PTFE has the lowest coefficient of friction of synthesized polymers, of 0.02. FEP comes in close second with 0.04, which is 5 to 10 times lower than some of the commodity materials available. The lower coefficient of friction, the more lubricious material is. FEP is definitely, for the lack of a better word, slippery. FEP, similarly to PTFE, has very good temperature stability with maximum service temp of 200 Celsius. It has excellent dielectric insulation properties with dielectric strength of 2,000 volts per mil. It has great chemical inertness and UV transmission, which leads to excellent weathering properties. It has lower gas and vapor permeability than PTFE, as well as low absorption of solvents, which contributes to the superior performance of FEP over PTFE in some applications. FEP also has exceptional translucency compared to the other plastics, and it is definitely more transparent than PTFE. Now on to FEP heat shrink. Traditionally, FEP heat shrink has been limited to 1.6 to 1 recovery ratio on the highest end of the expansion. But the envelope can be pushed, and with the right sizing considerations, FEP heat shrink can be expanded to as high as 1.8 to 1. One of the major differences between PTFE and FEP heat shrinks, however, is their recovery temperature. PTFE recovers around 343 Celsius, and we suggest 215 Celsius for a successful FEP recovery. FEP, and any heat shrink for that matter, that process has to be developed based on particular needs of applications. Being a fluoropolymer, FEP is extremely chemically inert. On the other hand, if the heat shrink's surface has to be bondable after recovery, chemical etching process can be employed to achieve a reactive exterior. So now imagine a combination of PTFE and FEP heat shrinks. What if we had an exterior PTFE layer and an interior FEP? The dual shrink is just that. It is a well-designed combination of PTFE and FEP in a shrinkable configuration. PTFE is the outer layer and FEP is on the inside of the tube. When heat is applied, PTFE recovers and reflows the FEP portion. FEP has a melting point of approximately 265 degrees Celsius. At the end of operation, the substrate is fully encapsulated by the FEP and has a tightly fit PTFE layer on the outside of the assembly, as seen on this image. This solid encapsulation forms a hermetic seal with excellent moisture barrier properties and a very tight fit, where severe mechanical stresses, such as pulling or vibration, do not compromise the system. Because of the very high continuous use temperature for PTFE, the dual shrink has a service temp of 232 Celsius. So, different properties of PTFE and FEP are combined in the dual shrink. It has all of the outstanding chemical, mechanical, and thermal properties of PTFE and exceptional permeability resistance and dielectric insulative properties of FEP. As you can see on this slide, the dual shrink is a perfect combination of two very specifically engineered materials, and it augments potential applications because of such. In this table, the tensile properties as well as dielectric strength and deflection temperature are summarized for both PTFE and FEP. Clearly, the combination of these two materials with deflection temperature of PTFE, 140 C, and dielectric strength of FEP, up to 2,000 volts per mil, for example, create an unparalleled product. So, because of its linear structure with combination of engineered processing, PTFE can be peeled off at the end of application if the heat shrink is used as an assembly aid and is not necessary for chemical and/or mechanical coating in the end application. However, yet again, PTFE recovers at relatively high temperatures. This may be beneficial in some applications and detrimental in others. FEP has a lower recovery temperature set point. However, it is very difficult to remove post-recovery, especially when the substrate is comprised of softer material. When trying to skive FEP heat shrink off after the recovery, one runs the risk of damaging the underlying shaft and scrapping the whole assembly. To combat such production issues, evolution of fluoropolymer heat shrinks has allowed for engineering of fluoropeels. It is an FEP derivative heat shrink that is fully comprised of fluoropolymer matrix. It combines the peelability of PTFE with lower recovery temperatures of FEP. It is ideal for a system with lower durometer and lower melting point substrates. It is recommended to slit material prior to recovery for easy peel tabs to be available post-application. Fluoropeels can be easily removed by pulling on those tabs. The heat shrink peels off cleanly and effortlessly, no matter the length of your assembly. Because fluoropeels is a fluoropolymer derivative, it possesses low coefficient of friction, very good chemical resistance, low solvent absorption, and very good temperature stability. Though slightly lower than FEP, fluoropeels has its operating temperature at 190 degrees Celsius. It may be useful if some or all of the material remains on the assembly for application use. As I already mentioned, fluoropeels has longitudinal peelability along continuous lengths. If application calls for visual monitoring of the reflow process using the heat shrink, it is important to notice that fluoropeels has exceptional clarity with haze and diffuse transmittance values as low as 6%. Fluoropeels can be consistently expanded up to 140% of its original diameter, hence the 1.4 to 1 recovery ratio. However, the very property that makes it so attractive in the end can make it very difficult to expand to very high ratios. After all, the tube peels. However, in certain sizes, fluoropeels can be expanded to as high as 1.65 to 1. For instance, an expanded 198 thousandths of an inch tube can be recovered down to 120 thousandths diameter. Wall thicknesses play an important role as well. For fluoropeels, a minimum wall thickness of 8 thou is recommended. As far as its recovery process, we recommend to begin around 215 Celsius with anticipation of adjusting this temperature down in the process development sequence. Shifting gears a little, moving away from fluoropolymers, but staying in the realm of highly engineered, superior performance materials. PEEK, polyether ether ketone. The aromatic structure of this material is shown on this slide. It is a semicrystalline thermoplastic that belongs to the polyaryl ether ketone family of materials. Polyether ether ketone contains two ether linkages and a ketone as shown on this slide. The ethers are identified in brown and the ketone is in blue. Because of the aromaticity within the structure of the polymer, it exhibits properties unseen elsewhere in the polymer world. PEEK's superior properties include very high service temperature of 260 degrees Celsius. It also has outstanding chemical resistance, including solvents and various fuels. It retains its properties even post 3,000 autoclave cycles and is resistant to gamma radiation, which makes PEEK very attractive for medical applications. It has excellent combustion properties with the UL94 rating of VO. It emits very little smoke or toxic degradation products when exposed to flame. PEEK also has exceptional toughness and tensile properties. Here we see tensile strength versus temperature curve for PEEK. As one may see, the tensile strength does change when heat is applied. However, the mechanical strength remains very high, up to 232 degrees Celsius. At room temperature, PEEK has tensile strength over 10,000 psi. Very impressive for a plastic, for sure. It is important to remember that this data was collected on plaques made to an ASTM geometry and not on tubular specimen. From the tensile properties perspective, when PEEK shrink was tested, striking results were observed. We will talk about those in just a few moments. Let's talk about the recovery process for PEEK shrink. Development of such for heat shrinks requires understanding of the end goal and final performance characteristics desired in the assembly and product. Because PEEK is a very versatile material with mechanical properties ranging widely, it is essential to begin with the end in mind. Here are some pointers for such system development. First of all, recovery ratios. PEEK can be expanded up to 1.4 to 1 ratio, with expanded ID ranging from 0.38 to 2.5 inches, and recovered wall of tubing between 4 and 10 thou. Our recommended recovery temperature for PEEK shrink is 337 degrees Celsius, and PEEK melt around 343 C, making recovery process very important. It is also important because PEEK is a semicrystalline material with very different properties in amorphous versus crystalline states. We discussed some of them already, but let's take another look. The so-called translucent recovery is achieved when material is subjected to temperatures as high as 340 C. However, one can further heat the material and obtain a recrystallized product. Material will become opaque, and this difference in crystallinity will result in different properties. One of the most interesting and useful properties of PEEK shrink is its ability to bond to metal substrates when recovered under certain conditions. Creating the bond begins with opaque recovery conditions. However, post-recovery heat may be necessary as well. I had mentioned such diverse mechanical properties of PEEK, which are heavily dependent on processing. Here we are comparing tensile properties of PEEK tubing and PEEK shrink when recovered and when recrystallized. Note that this data was collected on non-ASTM geometry and should be used for comparison purposes only. Taking a look at the modulus for amorphous PEEK, crystalline PEEK, recovered PEEK shrink, and recrystallized PEEK shrink, we see a drastic difference in the values ranging from above 2,300 megapascals all the way up to over 9,000 megapascals for the recrystallized material. Stress at yield, elongation at yield, stress at break, and elongation at break change with processing as well. Crystallinity state of the material as well as the recovery conditions are very important in achieving appropriate results in the end application. Processing of heat shrinks can be an intimidating task. Here we're going to discuss what questions to ask and what specifications to put in place in order to have a successful recovery process. First of all, sizing of the heat shrink. One should understand what wall thickness is needed and if the material is going to remain on the substrate in the end use and application. Evaluating the substrate will lead to the expanded and recovered dimension specifications as well. Longitudinal change is of essence as it is inevitable in a heat shrinking process. Understanding that fluoropolymers will have less of longitudinal shrinkage than, let's say, PEEK shrink is of essence as well. We will discuss combating longitudinal change in a few slides. Size of your mandrel and all of its dimensions are attributes to consider during the sizing step of the process. Whether the mandrel has any tapers, transitions, or other irregular shapes which may need to be covered is of utmost importance. Most heat shrinks will create a very tight barrier layer when sized appropriately. What about composition of your mandrel? What temperatures can it withstand? Can you accommodate for slight softening of the material and potential dimensional change of such? One must understand the purpose of the heat shrink in the application. Is it going to remain on the assembly and perform a function post-recovery? Does the material need to perform as a great insulator? Or is it going to be stripped off at the end of the thermal cycle? After some or all of these questions, one can begin the processing considerations. But first, the heat source. There are many ways to recover heat shrinkable materials. High-performance heat shrinks require more attention to the heat source, however. Heated blocks, ovens, or any traversing heat source can be applicable. Each has its own set of questions. For heated blocks, for instance, it is important to know the size of the heat shrink, so one can engineer appropriate size of the block opening. This method of recovery appears to be the most consistent, especially if sized correctly. However, it may not be feasible in certain production situations. Ovens, especially convection type, provide even heat around the part, which results in uniform recovery, but sizes of the oven will restrict the largest size of the part one can produce. Therefore, traversing heat sources, where the heat is localized and concentrated with a nozzle or a deflector, may be a viable option. It is important to understand that the set point of the heat source may not reflect the actual temperature at the part. Therefore, material may not recover uniformly or as rapidly. We recommend the following temperatures for different materials as listed in this table. Heat source and temperature are not the only factors in the recovery methodology. Speed at which that temperature is applied is important as well. For instance, FEP begins to recover almost immediately at its recommended temperature, while peak may take up to 2 minutes before it starts to move. It is all about the balance of the heat that is applied and the time that material is held at such temperatures. The amount of thermal energy put into the system must be enough to recover the heat shrink, but not damage any of the components of the underlying material or the heat shrink itself. Speaking of the temperature of recovery, the set point of your heat source may not, and generally will not, correspond to the exact temperature material is experiencing. Mandrels are generally a heat sink in the system, which lowers the overall temperature of an oven, for instance, when introduced inside of a such. Preheating the mandrel may overcome such a drastic temperature dip. On the other hand, if using a more concentrated heat source, for instance a heat gun, you may need to set the temperature on the controller to 290 degrees Celsius for an FEP recovery process, because you will move the heat source along the length of the tube, and the heat shrink may or may not reach the full 290 C in the process. Some processes have been developed where a very low heat-resistant material, such as lower degradation temperature polystyrene, has been covered with a very high temperature heat shrink, such as peak shrink, without any damage to the substrate. It is definitely all in the process. One last point, longitudinal change. This has to be of high consideration when developing a thermal process for heat shrinking. One of the most important things is material specifications, sizing to be exact. If longitudinal change is not incorporated into the material specification, one may try a weighted recovery when one of the ends has a weight affixed to it, which would prevent the heat shrink from a drastic longitudinal shrinkage. On the other hand, longitudinal growth during the process will be augmented using this technique. Another way to combat longitudinal change is pre-shrinking the ends of the tube over the mandrel. That allows for a more uniform, steady recovery of the heat shrink. As you probably noticed, there are so many parameters to consider when deriving engineering specifications to the heat shrinkable tube, as well as developing the process to use the heat shrink. Different applications call for different attributes as well. But we can most definitely say that there is a world of possibilities of heat shrinks, and this world is tailorable to your specific needs. And now back to Matt Allen with a few closing remarks.
Thank you, Dr. Roof. We've covered a lot in a short period of time. To summarize, no matter if you're drilling for oil, building a plane, or constructing a catheter, there's a world of possibilities for high-performance heat shrink applications. Zeus is staffed by a host of technical resources who are ready to answer your questions. We want to thank you for attending, We ask you to please stick around after the Q&A for our survey and a chance to win a pair of Bose noise-canceling headphones.
Okay, Wayne, Matt, and Irina, thank you so much for that informative presentation. Now, before we get to the questions that have come in from our attendees, let's make sure everyone knows that if we don't get to your question, don't worry. We'll have an answer for you within 24 hours. The complete Q&A transcript, including answers we did not have time for, will be sent to all of our registered attendees and will be posted with the webinar when it goes into the on-demand mode. Okay, now on to our first question. Wayne, this first one looks like it's for you. What is the most optimal way to recover heat shrink?
All right, to repeat the question, what is the most optimal way to recover heat shrink? Well, as we discussed earlier, that will depend greatly on the material and the manufacturing conditions. Safety is first, so we recommend working with the manufacturer to determine the material you are trying to heat shrink, any venting needs for safety, and some recommended temperatures. Once you have found the needed temperature arranged to recover your product, we recommend a convection oven for the best and most uniform way to recover heat shrink. Just like baking a cake, you need consistency. With an oven, you have a uniform temperature that stays at that level through the duration of the heat shrink process. A good oven can handle both high and low temperatures consistently, therefore offering one option for a variety of heat shrink materials. Also, if you want a continuous process to increase efficiency, various manufacturers make conveyor ovens which allow you to use a continuous process without sacrificing temperature consistency.
Irina, why don't you take this next question? What materials can be made into heat shrink?
Well, just about any elastomer can be made in a heat shrinkable form. Process development is key for a successful not only expansion but recovery as well. However, the recovery ratios may not be the same for all materials. It is important to keep in mind desired performance characteristics of material itself, as well as recovery process, which has to be tailored to the application. Interestingly, process development must consider cross-linking as well as other parameters in order to produce a heat shrinkable tube. For instance, PVDF or PBAXs may present a challenge to make into heat shrinkable form because of the cross-linking material requirement to lock in their elastic memory.
Okay, let's take a look at another question. Can FEP heat shrink be supplied scored so it's easier to remove? Matt, why don't you answer this one for us?
Absolutely. Scored FEP heat shrink is available. However, thinning of the heat shrink wall will affect the reflow characteristics of the system, leaving undesirable surface defects. Those include surface imperfections such as longitudinal lines on the assembly and other non-uniform blemishes. To combat those imperfections, a non-mechanical solution was developed. Fluoropeels, a derivative of FEP heat shrink, recovers at similar times and temperatures, and once notched on one end, can be peeled longitudinally continually down the length.
Okay, Irina, this looks like another one for you. How can one control longitudinal change in heat shrinks?
First of all, material considerations are essential. While some fluoropolymer heat shrinks can have controlled longitudinal change of plus or minus 5%, PEEK, for instance, is a common offender for longitudinal change being higher than 10%. It is important to begin with the end in mind. Is longitudinal shrinkage a problem for your application? Can you accommodate for longitudinal growth? Some of these parameters can be dialed in during the manufacturing process. Then, of course, your recovery process is important as well. We touched on some of the ways to combat longitudinal change in the recovery process. For example, weighted recovery, preheating the system, or tacking the ends are just a few starting points. So, material choice, processing parameters, and recovery method are all important factors in regards to controlling longitudinal change.
Okay, here's another question. How is color affected by heat shrinking the material? Wayne, can you answer this one for us?
Great question. That will really depend on the material. Fluoropolymers such as PTFE, FEP, and PFA can easily have color added to them for part identification or marketing purposes. Designers should note how the color looks after recovery versus in its expanded state. Color pigments are added to the tubing typically during extrusion and processing. Then the tubing is expanded. The expanded process stretches the material, therefore making the color seem less dense or brilliant. However, once recovered, the material and color should return to its original state. Color Pantones can typically be matched on fluoropolymer heat shrink plus or minus a shade. However, note with your manufacturer the need for colored material that is translucent versus opaque with fluoropolymers. Fluoropolymer heat shrink can be made, for instance, blue in both opaque and translucent forms, so be specific as your application demands. Peak shrink is one material that can have some translucence transitions even if no color is added. As Dr. Roof mentioned earlier, depending on how long the material is exposed to heat, it can be more translucent tan by appearance for short-term exposure to heat, or very opaque with no translucence if it is heated long enough during the recovery procedure.
Okay, we have time for one more question. Irina, this last one is for you. Does wall thickness affect my reflow process?
A lot of times, fluoropolymer heat shrinks are used as a reflow aid in the catheter construction process. That's from where I'm assuming this question's coming. Yes, absolutely. Wall thickness of the expanded product as well as its recovered dimension play a huge role in the way material underneath the heat shrink reflows. Also critical to the process is sizing of the heat shrink and the substrate. From the physics perspective, wall thickness is going to change the thermal mass, which is moving during the shrinking process, which in turn is going to affect the recovery force, or hoop strength, of the tube. So it is crucial to size the heat shrink, understanding what the final dimensions of the shaft ought to be. Of course, the whole system must be considered. At times, the reflown substrate is the deciding factor of the consistency of the final product, versus the wall thickness or any other characteristic of the heat shrink.
Well, we're going to have to wrap up this webinar right there. Wayne Black, Irina Roof, and Matt Allen, we want to thank you so much for being here and sharing so much great information. And thanks to all of our audience members for being part of this webinar event. Now, we'd like to ask that you fill out the survey that will pop up on your screen at the end of this webinar. As a sign of our appreciation, one lucky attendee who takes the time to fill out our survey will have a chance to win a pair of Bose Quiet Comfort 25 acoustic noise-canceling headphones. Again, thank you for taking the time to join us for this webinar event. Take care, and we'll talk to you soon.